Okay, so obviously we already know that something can't move in a circle without a force pulling it towards the center, because that causes the centripetal acceleration, that causes the change in direction. She swallowed the spider to catch the fly, and yeah, okay, one thing causes the other. All right. We need to understand that lots of forces can act as a centripetal force, and that's kind of the challenge in this unit. This unit's not mathematically difficult. Okay. But what we're challenged with in this unit is identifying what's acting as our centripetal force. We already said that for a car going around an unbanked corner, the centripetal force is being provided by friction. Okay, for the moon, it's gravity. Okay, we have to be able to identify the centripetal force. Okay, because the centripetal force is causing the acceleration. In the last unit, what force always caused the acceleration? The net force. So centripetal force is net force. Okay, that object won't travel in a circle unless the sum of all the forces is towards the middle. Right? Now, very rarely do we have like lots of forces trying to pull it in different directions. That's not likely. Okay, but the centripetal force has to be the net force directed towards the center. Now, in the last unit, we calculated F net by going m times a, or by the vector sum of all forces. In this unit, similar, except now it won't be acceleration in general, it'll be centripetal acceleration. And the formula for this is v squared over r. So in this unit, this looks like this. That'll be the formula that you use as often as you used m times a in the last unit. Okay, that is our net force formula for something moving in a circle. Okay, and as we said, our challenge will be to determine what force or forces are acting as the centripetal force. So early on, when we're talking about just uniform circular motion, this will be provided by one and only one force. When we start getting into non-uniform circular motion, then we'll have some forces that act directly in and some that act directly out. And then we'll have to subtract them because it'll be the vector sum of all forces. Okay? So nothing different than we did in the last unit, just now applied to a circle. Okay, so we're going to look at how centripetal forces operate. Generally, they pull things towards the center. Okay, that's their job. And we're going to look at how banked curves use Newton's third law to produce greater centripetal force. Okay, now a bank curve is like the on-ramp or off-ramp of an interchange, like what we have out here to get onto Highway 2. Okay, we bank curves because that helps us to traverse those curves, but it also guarantees a safe speed at which you can take that corner, regardless of the condition of the road. Okay, banking a corner can make it possible to not require friction to make the turn. Okay, you can be completely unrelying on friction. Now, out there, that exit ramp, the exit speed is, it's what, 60? No, the big one out there. 50. No, it's not 80. I'm pretty sure it's 60. Yeah. Okay. Yeah, where you get on to Highway 2. No. Okay. Whatever it is, see, that's how bad it is. Like I don't even care what it is. I just know how to go around it. But if I go around that corner at more than the recommended speed, as long as it's not ridiculous, I still stay in the corner. It's just now I'm also relying on friction. I'm not just relying on the corner's design, I'm relying on friction to keep me from sliding out. Okay. If it's covered in perfectly frictionless ice and I go too slow, I can slide in. I've seen it happen. It looks really weird, but actually being overcautious when the road is really slippery can be just as bad as having a lack of caution. Okay. In fact, it might even be worse because there's no guardrail on the inside because nobody would possibly lose it on the inside of the corner. Okay. And the only way they can is because they're going too slow. Okay. Like the person in front of me, I actually went out around them because I knew what was going to happen to them. I could see them starting to slide. And I'm like, they're going too slow. So I went out around them so I could go exactly the right speed so that I wouldn't slide either way, right? But they were going so slow, and then once it started, there's nothing they could do because they didn't have enough traction to speed up anymore, and right into the middle. Well, because it's physics, and I'm like, yeah, superior. Yeah. And, yeah. You didn't take my physics class. Had you, you wouldn't be in the ditch right now. No. Okay. So Newton's second law says that obviously whenever an object accelerates, there's a net force causing that acceleration. So we've said that about 4 times already today. Okay. This is also true for circular motion, which is why we have this formula here. It's mass times acceleration, but it's defined for a circle, so it's mv squared over r. Okay, that's going to calculate our centripetal and thus net force for an object moving in a circle. Okay. All right, so in lots of cases, it's easy to identify the centripetal force. Okay, if I've got something tied on a rope and I'm swinging around the circle, obviously the rope is the thing that's keeping it in the circle. Okay, a car going around a corner, friction, fairly obvious. The moon going around the Earth, gravity. Okay, less obvious because there's not an actual physical connection there, but okay, obviously that would be the only force capable of doing that. Okay, but sometimes it's a little bit tricky to kind of determine what force might be causing that object to turn. Okay. All right. So first thing we want to look at is the effective speed on centripetal force. If we're just looking at the formula, as we already said, speed would have what effect on Fc? An exponential effect. If I double my speed, I'm going to require 4 times the centripetal force. Think about that when you're going around an unbanked corner in town. Okay? If it's supposed to be taken at like 30 and I take it at 60, I'm hoping and praying that friction can provide suddenly 4 times as much force to keep me in that corner. What's the likelihood of that? Not good. Okay? Especially if it's icy or covered in all the little rocks that they haven't swept up yet. Okay? Because that can also affect it, right? It's very easy to slide if you get into those rocks. Off you go. Okay, it's not a clean rubber to asphalt surface. Okay? So we have to remember, obviously, that speed has an exponential force or an exponential effect on this, and we can prove that right now. Okay, we'll do this plane. Okay, at different speeds. So the mass is 0.9 kilograms. All right, so we'll go Fc for the 19 meter per second. So we'll go 0.9 times 19 squared divided by a radius of 17 meters. All right, so we're looking at 19.1 newtons worth of force here. All right, if I do that for twice that speed, so 38, okay, I'm going to have 0.9 times now 38 squared divided by a radius of 17 meters. All right, 76.4, exactly 4 times what I got before. Okay, so definitely has an exponential relationship, okay, between speed and centripetal force. Okay, questions on that? Okay, so we've got, oh, sorry, that's the math we just did, sorry. Okay, radius, we've kind of already looked at that. We looked at it with centripetal acceleration. The relationship is exactly the same with centripetal force. Okay, I'm going to have an inverse relationship. So if I've got a radius of 11 and a radius of 22, then my centripetal force for the 22 meter circle will be how much of the 11? Half. Okay, it'll be half because I will have a much wider arc that I'm traveling through, okay, and require less centripetal force. Now that's a little bit odd, okay, because we watched those merry-go-round videos, remember? We all got a good laugh out of all the idiots, okay? It was, the people were trying to stay near the center, yet this formula says that if I increase the radius, it should be easier. What's the flaw in that? Well, no, I mean, not really. Which one has a bigger effect here? Speed. So the further from the center I get, the faster I'm going if I'm on a merry-go-round. Okay? Yes, radius is increasing, but this has an exponential effect. This doesn't. Okay? So the further out on the merry-go-round I go, the worse it's going to be for me because this plays a bigger role in how much centripetal force I need than this does. Okay? Everyone all right with that? All right, so this is the math of it. Okay, for the radius of 11 meters, I needed 64 newtons worth of force to stay in the circle. I double that radius. I have half the centripetal force, okay, required to stay in the circle. All right. So when we come back from Easter, we're actually going to be doing a couple of labs. One lab on speed and radius, and then another lab on speed and centripetal force. Okay, so we'll be whirling some stuff around in circles. Okay, we're going to really test your hand-eye coordination, okay, on those two labs. You have to, you'll have a plastic tube, and you'll have a weight attached by a string through the tube to a rubber stopper. You cannot hold the string. You can only rotate the tube. None. I have one person get a shiner once, okay, and that's because they were doing this. They were rotating the rubber stopper, and they were trying to watch it. Up here, okay, yeah, up here. That's where you want it, okay, yeah. So that's the only time anybody's ever got hurt. If you think you're going to get hurt, I will go get you some goggles from the lab, and you can wear the safety goggles while we do this. But I think it's a little bit unnecessary. Okay, so if I have a car that goes around this corner, okay, I'm relying on the force of static friction. Static friction, not kinetic. Okay, if I'm relying on kinetic friction, what are the tires doing? Skidding, they're sliding. Okay, if I drift to this corner, then I'm relying on kinetic friction. Okay, but remember, kinetic friction's always lower than static. So you're better off to take the corner without sliding than you are to take it while sliding. I'm not saying it will be as fun or look nearly as cool, but okay, it will be faster, okay, to do it that way. All right. The other issue with drifting a corner, and the reason that drifting kind of works, is because you actually rotate the car. Okay? And when you rotate the car, you're actually spinning the back wheels and making them push which way? Inwards. Okay? So your inertia wants you to do this, but you've turned the car to provide an angled force, so the two things are kind of canceling off and causing you to at least go somewhat in a circle. Okay? Somewhat in a circle. Okay. All right, so we do want to rely on, like we say, static frictional force. If we lose that, then we're relying on kinetic, and we're just going to slide. Okay, we're going to slide out of the corner and hit something. Okay, we don't want to do that. All right, so here's what we're going to do. We're going to look at how that exactly works. Okay, what keeps me in an unbanked corner? Friction. All right, that means then that my centripetal force is being provided by the force of friction. All right, so what I've just done there is the vector sum of all forces. Friction's the only force. Okay? Gravity and normal force don't really matter here because they're vertical and they cancel. It's a level surface. Okay? So I've got these two forces equal to each other. So that's going to mean mv squared over r equals, what's the formula for the force of friction? Right, mu times the normal force. All right, since this is an unbanked corner, it's level. Normal force is equal to gravity. So I can alter this and I can say, all right, as long as I know the radius of that corner and the coefficient of friction, can I calculate the maximum safe speed? Yes, I can. I just manipulate for velocity. What is going to happen when I start manipulating? The m's are going to cancel. Okay, this is where perfect physical world is a lot different than the real world. Okay, in the perfect physical world, it doesn't matter whether I've got a really heavy vehicle or a really light vehicle. They would take this corner at the same rate. Obviously, in the real world, that's not the case. Okay, in the real world, we have more masses, more inertia, wanting to go in a straight line a lot more. Okay, we've also got the distribution of that mass that can factor into roll. Okay, and that's actually what leads a car, any car, to lose it on a corner, is they start to roll, which means they lose that normal force being on one set of tires. It transfers just to the other set, and they start losing it, right? They get this directed force that's kind of lifting them off, like when we were pulling the box at an angle, and then they start to lose it, okay? And that's because of this inertia stuff, but we're simplifying, okay? If I want to solve for V, I'm going to multiply both sides by R. M's going to cancel, and then I'm going to take the square root. So V will equal the square root of mu gr. Mu gr, right? Mu gr. All right. So if I plug in my numbers here, okay, I know the radius is 50 meters. We'll calculate this for dry weather first. Okay, so V for dry weather is going to be the square root of 0.9 times 50 times 9.81. All right, so the maximum speed under ideal dry conditions for the car to negotiate this corner is 21 meters per second. That's not half bad. Okay, it's like almost 80 kilometers an hour. So not too bad. I think it's an Eclipse, like an old one, like a 92. It's still got the bump. All right, yeah, so if, however, I'm under icy conditions, I now have 1/9 the available friction. How much slower am I going to have to go? Remember, speed's exponential. I have 1/9 the available friction. No, other way. The square root of 1/9 is 1/3. Okay? Yeah, so I'll have to go 3 times slower. Okay, now that I have 1/9 the available friction. Okay. All right, so V in this case, okay, so V for icy conditions, we'll have 0.1 times 9.81 times 50. Okay, exactly 1/3. Okay. I have less friction, I can't go as fast. Okay, something we all need to remember next winter. Hopefully not again this spring, but you never know, right? We still could get snow because, well, it's only April, and we can get snow any month of the year here. Okay, just got to be ready all the time. All right, questions on how that works? Okay, so basically everything in this unit is going to work like that. Determine what's providing the centripetal force, set them equal, manipulate and solve. Okay, so sometimes that force might be gravity, sometimes it could be friction, sometimes it'll be something else. You just have to put them equal to each other and manipulate for what we're looking for. Okay, so that was just the math that we just did, okay, and those are the answers that we got. All right, banked curves. Okay, we bank a curve so that we can use some of the normal force that acts on a bank to help direct us back towards the center. Because a bank curve is really just an inclined plane. Okay, it's just wrapped around an axis. So it's kind of like a screw, right? Because that's what an inclined plane wrapped around an axis is, a screw. That's why Sheldon Cooper always tells people, you're an inclined plane wrapped around an axis. You're screwed. It's a Sheldon Cooper joke, but it's funny. I think I've used it once before. You guys don't look shocked on that one. Okay, so we've got this bank. Okay, if we're talking about a roadway bank, it looks like this. But this is also how planes turn. Okay, if a plane wants to turn, it actually has to dip its wing, right? Dip the lower wing and use the lift provided by the wings to push towards the center and cause it to turn. Right? Now, this is also how they lose altitude, because once they dip one wing, now the lift isn't directed upwards anymore. So there's not as much force keeping them airborne, and they lose altitude. So as they're coming in for a landing, you've probably noticed if you've ever flown, they tend to go in a bit of a circle, okay, until they get to a low enough altitude to be ready to land, right? They're just slowly banking and losing altitude by doing that. But banking the wings creates at least some force directed towards the center, because the lifting force is directed straight out from the wings, and it has a horizontal component that keeps it turning and a vertical component here. Now that vertical component, once we're banked like that, is no longer equal to gravity, which is why we lose altitude. Okay, so a plane can't stay in a bank forever. Okay, it eventually has to right the wings and get some lift back. Okay. Same is true for a banked curve. Okay, a banked curve works just like an inclined plane. Okay, so if we think back to last unit, the forces involved on an inclined plane are gravity. Gravity pulls us into the plane. Okay, what happens with that is the plane pushes this way. We never drew it this way. We always drew the normal force down below. Okay, but this is the direction the normal force acts. Okay, it pushes this direction. Now, if I go faster, okay, this is just if the car is sitting there. But if I'm actually going around the corner, do I cause more normal force? Yes, because my inertia wants me to go in a straight line. That would be this way. So there's also some normal force created from my inertia pushing on the road. That can actually make this normal force bigger than gravity. Okay, and so now what I end up with is, here's my normal force. Okay, I've got gravity going this way. Okay, and I've got the horizontal component here. Okay, so I'd have a horizontal component. This angle here would be the same as this angle. Okay, whatever the angle of bank is. So this side here would be equal to gravity. This side here would be directed towards the center and is providing my centripetal force. Okay, that's keeping me in the circle. Yeah? All right. It's a little bit crazy, but this is how city planners and overpass designers have to think when they're designing an interchange. Okay? They know how much room they have to work with. So they essentially know what the radius of their corner is going to be. All right. From that, they can determine, all right, how fast do I want people to take this corner at? How steep do I need to bank it? Right. Now, we're not talking about an extreme bank. No interchange is going to have a bank that's a double-digit number. All right. If we think that 9 degrees doesn't seem like much, but 9 degrees is really steep. Okay. Like if you were just sitting on a 9-degree incline, it would feel steep. Okay, it would, and you'd be likely to slide down it. Right. So we don't bank things a whole bunch. NASCAR, on the other hand, okay, their corners are extreme. In fact, in order to pave these corners, they have to park a crane on the other side of the corner and extend the boom out and hold the paving machine on the corner with the crane. Otherwise, the paving machine will tip over and slide down into the center. Okay, they're banked that much. Would they have to section it? Would it not just all slide down to the bottom and sink there? Well, it's asphalt, right? It's not concrete. Pouring, yeah, asphalt's stickier, so it probably sloughs a little bit. They probably have to make it so that it's a certain temperature and sets up pretty quickly. They'd basically never be able to do this with concrete, because you're right, it would just slide down, right? Now, you can still do stuff like that with concrete, but you've got to put lots of calcium in it so it sets really fast. And that's what they do if they're making like the LRT tunnels, right? So they would have the form there, and that stuff needs to set up like that, right? Yeah, it needs to set quickly.
So when like a car crash, like it's kind of just losing like friction, right?
Mm-hmm.
So why do some of them like they don't get hit that hard right on the car, but they still lose all the friction?
They don't have to get hit that hard. If they get even tapped from behind, it's just like a pit maneuver, right? You give them that little nudge that causes them to lose the static friction, then suddenly kinetic friction is not enough, and it just gets out of control really fast. Okay, getting tapped from behind by another car can cause you to go faster than the tires are spinning. That starts the slide, right? Then again, static friction is gone. You're relying on kinetic friction, and it's not enough. And other times it can just be that they tap you on the corner, like the pit maneuver, and get you moving in the wrong direction. Okay, then you can't recover, right? Most of the time, like with a pit maneuver, they push really hard and they actually rotate you completely. Okay, in NASCAR, they just kind of tap you a little bit and it starts because you're going so fast, right? And lots of times with NASCAR, you see them after they hit the wall, they slide down to the middle, right? There's that much bank, right, that they'll slide back to the middle. Mm-hmm. All right, so this is what we're looking at here is this relationship. That's what's got to be determined by a roadway designer is what angle do I need to bank this at for this speed and this radius. Yep, yeah, same thing, right? The more we bank a corner, the faster you can take it. If you watch that indoor cycling at the Olympics, same thing, like those tracks are extreme, right? That's why when they're just warming up, they're never actually up on the corners. They go on that single lane that's in the middle that's not banked. Okay? It's hard. You have to go really fast in order to stay in those corners. No, like you want to be as close to the inside as you can without losing it, right? Like that's what a race car driver has to do. They have to, so they look at a corner, okay, like this. They don't just pick the middle line and go around it. They start way out here and they pick that line that goes like this, right? Because essentially what they've done then is they've made the radius of that corner bigger. If they'd have gone this way, that's a much smaller radius, right? A straighter line means I need less centripetal force because it's not really a corner. It's more closer to a straight line, right? That's why they come in high and they go out high, right? It's widening, increasing the radius of the corner, meaning they can go faster. Okay? If they don't pick that right, that's when they can lose it, right? If somebody's passing somebody on one of these corners, they have to pick the line, right? They're either going to pass them on the outside or they're going to pass them on the inside. Okay, if you pass them on the inside, you've got to, if you lose it, you're going to take them out too. If you pass them on the outside, then you just go into the wall, right? So yeah, it's there's a lot of experience and practice that goes into doing that correctly. Right? It's not something you or I could just drop down behind the wheel and go, I'm going to do this. Okay? Yeah. We'd be like Ricky Bobby after his accident, right? Were those the other cars? Were those the other drivers? Yeah, they would have to make sure not to lock up the wheels. If they locked them up, then it's back to kinetic friction, which won't be enough. If that happens on a corner, they're very likely to go out. Happens on a straightaway, not as big a deal, right? You're going to slow down. That could cause an accident behind you, but you're not likely to go into the wall. Okay, so if we're looking at this relationship, so this is kind of what I just drew here, right? We've got normal force acting straight out. There's a vertical component to that, which I'm actually going to draw over here instead because it makes more sense over here, okay? That will be equal to gravity. That keeps me from falling into the corner, keeps me from flying upwards off the corner, okay? And then there's this horizontal component of it that is acting back towards the center, right? So the angle of bank is related to these two forces. Okay, how much I bank the corner is related to these two forces. So what we're saying is this force is the vertical component of normal force, Fn times the cos of theta, and it's equal to the force of gravity. So m times g equals normal force times the cos of theta, because it's the adjacent side. This is going to be the opposite side, because it's actually up here. All right, so sorry, I'm going to draw it over here now. Draw it on that one. So gravity is the adjacent side to the angle, and this centripetal force is the opposite side to the angle. Everyone okay with that? All right, so centripetal force is mv squared over r, and that equals Fn times the sine of theta. All right, if I want to determine that angle, and I know these two sides, what trig function do I use to get the angle? Tan, because I have opposite over adjacent. Okay, so here's what we're going to do. We're going to derive the formula for a bank curve, knowing that this is my opposite side and this is my adjacent side. Okay, so I'm going to say mv squared over r divided by m times g equals Fn times the sine of theta, opposite side, divided by Fn cos of theta. Okay, everybody all right with what I've done? All I've done is take those two formulas and set them down here. All right, what's Fn divided by Fn? 1, so it's gone, right? Cancels itself off. Okay, and we just said this is opposite divided by adjacent, which is tan. All right, so the tan of that bank angle is equal to mv squared over r divided by mg. What happens to m? Okay, so really what I'm looking at is this. V squared divided by r times g equals the tan of theta. This is the formula that a roadway designer uses to determine the banking angle for a corner. Or, if they know the banking angle, to determine the speed limit for that corner. Okay? And that's how they derive it. It's related to those two things. It's related to gravity, and it's related to the centripetal force.
So since the masses like in the actual road have to be calculated, and there's such big range of like how much vehicles weigh, how would they like how to pick one?
They don't need to. Mass cancels.
Like,
The angle of bank is independent of the mass. That's why there's only one speed limit. If mass mattered, and even in the real world it doesn't, okay? I mean, rotationally it could. If you're a truck driver, you got to be smarter than, okay, I'm going to flirt with taking the maximum speed around this corner. You go slower, okay? But in the real world and in the perfect physical world, mass cancels. So I only need one speed limit because the angle bank is independent of the mass, right? All things accelerate at the same rate.
what if it's not that?
Well, if it's not banked, well, mass still canceled, right? But again, we said, yeah, that's fine if everything's center of mass is distributed the same way. In the real world, it's not, and things rotate. That's not due to friction. That's due to a rotational inertia, not the amount of friction available. Right? Okay, so that's our bank curve formula. It is on your formula sheet. Okay, it's not labeled bank curve formula. You'll have to remember that that's what it's for. Okay, but that's the formula that we'll use when we're talking about bank angles. Okay, so this is me walking through the derivation just in the note form. Okay, so FC was the opposite side. Okay, gravity was the adjacent side, which is how we derived that formula there. Okay, so what that tells us is that the given speed, okay, for a given speed, sorry, the centripetal force needed for a turn of radius r can be determined from the normal force, okay, and the banking angle, right? So it's independent of the mass of the vehicle. That's what's important. Once I go faster than that speed, then I'm also relying on friction. Now, friction is going to act this way because it's an incline, and friction acts downwards, down the incline. Okay? But it would still have a horizontal component that would act back towards the center. So when I start doing this for the real world and going faster than that bank angle, okay, FC would be then that force I calculate from just the bank plus. So I'd have the force of the bank plus the horizontal component of the force of friction plus. It gets really complex. Okay, we don't ever deal with that. All of our banked curves, will be frictionless. Okay, so they'll be just relying on the banking angle to provide that force. Yeah. Okay, so the purpose of a bank corner then is that we can provide we can have a speed limit that is safe regardless of the road conditions. Right? We don't bank curves so that we can take them faster. Okay, we bank them because they provide then a guaranteed safe speed to negotiate the corner at, even if the corner is covered in nearly frictionless ice. Right? That happens so rarely that it's not even a factor, but like I say, I've seen a car actually slide into a bank corner. Right? It's pretty rare, right? But it could happen.
If, per se, the corner was banked and it was covered in ice, you drifted to put the tires outwards rather than forwards?
No, they just wouldn't do very much because they would spin and there would be so little kinetic friction between them that they would basically do nothing. Right? Yeah, and in fact, usually if you start to drift like into the center, like to fall into the center, usually your car turns a little bit as well because the heavier part of it still has more friction. The engine over the front wheels, there's more friction there than there's at the back, so you do tend to rotate. especially since your panic reaction is slam on the brakes, cause the front end of the car to go down, cause that rotation, right? Okay, so if we're looking at this one here, we want to determine the angle at which a frictionless curve should be banked for a speed of 35 meters per second and a turning radius of 550. So we have R, okay, and we have V, and obviously we always know G is 9.81 unless we're told otherwise. All right, so we can calculate what theta will be. All right, so it'll be 10 to the minus 1 of this whole formula. So 35 squared divided by 550 times 9.81. Important that the bottom is done completely on your calculator. Okay? Otherwise, your calculator will do order of operations, and you don't want it to do that. Okay? So that'll give us a bank angle of 13 degrees, which is extreme. Okay? You would not bank a typical like civilian use corner at 13 degrees. Right? That's really, really steep. Okay? This is 35 meters per second, and a 550 meter corner is actually fairly small. Right? So an exit ramp that you can take at 130 kilometers an hour, okay, something like that. What's 35 times 3.6? 126 kilometers an hour. I mean, can you imagine taking that exit ramp out there at 126 kilometers an hour?
When you
Yeah.
have to speed up and you get down.
You'd have to slow down. You would, yeah. It'd be good though, because then finally people would come off of that exit ramp at the merging speed. Drives me insane when that people coming in there just driving Miss Daisy up the hill, and the rest of us are trying to merge, and they're going 80. Oh yeah, and the roads are terrible there. Yeah, and they got all those 2-lane roads that go through all these windy things. You're trying to pass somebody, but yeah, it's a mess. It can be, yeah, if there's nobody else on the road. Okay, so just a quick, this one here is just kind of a quick review of period and frequency, okay? So we got like a old-fashioned spinning hard drive, okay? So not a solid state drive, but an actual spinning hard drive, okay? They spin at fairly high speeds. The platter makes one complete revolution in 0.00833 seconds. All right, what did they give me here? It's the time for one rotation. What do we call that? Period. So this number is the period because it says it makes one complete revolution in this many seconds. So the period of the hard drive's rotation is 0.00833 seconds. They want us to determine the frequency in hertz and RPMs. What does RPM stand for? Revolutions per minute. All right, this is already in seconds, and I know that F is 1 over T. So when I do this, that'll give me this in hertz, or per second, cycles per second. All right, so all I have to do is go 1 over this, and that'll give me my cycles per second. So 0.00833. Whoops. I don't know why the 35 was there. 1 divided by 0.00833. All right, so that's 120 hertz. Okay, so this thing goes around 120 times in 1 second. Right? Now, it wants to know the revolutions per minute. So what do I need to do with that number? Right, multiply it by 60. Right, so that's 7,202 revolutions per minute, okay, for that spinning hard drive. Okay. So that was just to review this whole F is 1 over T, T is 1 over F thing that we talked about the first day. Okay, so we're not going to bother doing those. All right, so looking at this one here, so we talked about this situation earlier, pebble stuck in the tread of a tire, okay? It's 36 centimeters from the axle, so from the center of the circle. So what did they just give us there? They gave us radius. All right, so we know the radius of this circle is 0.36 meters, okay? And it takes 0.4 seconds for the wheel to make one revolution. What do they give me there? Not hertz, no. Period. And it's 0.4 seconds. Okay, what's the speed of the pebble at any instant? All right, what did we say our formula to calculate the speed of an object moving in a circle was? No, pi r squared gives me the area of a circle. d over t, right? V equals d over t. It's just I'm using the circumference of the circle as my distance because I was given the radius, right? So I don't actually use that. I'm using this version of it. So 2 times pi times 0.4 or 0.36 divided by 0.4. Okay, that'll tell me the speed of the pebble at any point along the circle. So 2 times pi times 0.36, okay, divided by 0.4. All right, so the wheel is moving at 5.7 meters per second at any one point. You don't. It asks for speed, right? I would have to know exactly where on the circle it was and then say, okay, well, that's horizontal or 30 degrees below the horizontal. I would never ask that, okay? Because you would, again, you have to know exactly where, and I'd have to give you the angle, and then what's the point of me asking if I told you the angle anyway? Okay, I want you guys to try these two. They involve using that formula there. With question number 1, the trick is they give us the speed in kilometers per hour. Okay, we can't use that until we got it in meters per second. Okay, so we just have to divide that by 3.6. Okay, so 261.0 okay, divided by 3.6. All right, so we got 72.5 meters per second, okay, as our speed. All right, and we're told that the wheels have a radius of 0.350 meters. Right, so we're looking for how much time it takes for them to go around one time. So we're looking for period. V equals 2 pi r over t. So we're just going to swap v and t here. So t will equal 2 pi r over v. So 2 times pi times 0.35 divided by 72.5. Right, and that'll give us our period of 0.0303 seconds. Right, everybody okay with number 1? Okay, so number 2, 2006, Alberta astronomer discovers the fastest spinning collapsed star, which we call a pulsar, okay, ever found. It has a radius of only 16.1 kilometers and is spinning at 716 hertz. Okay, so imagine this. You have something that has more mass than our sun, compressed into an area only 16.1 kilometers, okay, in radius, so only 32 kilometers across, but weighs more than our sun, and spins around 716 times in 1 second. There are some weird things in outer space, man, and pulsars are one of them. Okay, these are very, very strange objects. All right, so we are looking for its speed at its equator, which is going to be crazy fast. All right, so we're looking for v, okay, knowing that we have we have the radius 16,100 meters, because we'll need it in meters, and we have the frequency, 716 hertz. Now we said we could alter this formula to include frequency, because frequency is 1 over t. So really it's just this, 2 pi r times f. All right, that's the other version of that. So we take our 2 times pi times 16,100, and then divide that by 716. Sorry, multiply that by 716 hertz. Sorry. Okay, so we got 7.24 times 10 to the 7 meters per second. To give you some idea, or for comparison purposes, that's the speed of light. That's the speed at the equator of a pulsar. Yeah, if you were there, your perception of time would be different than ours because you would be going so fast. Of course, the last thing you would need to worry about if sitting on the surface of one of these things was your perception of time, that would be okay. The whole fact of being crushed and burned and vaporized all at the same time would probably be a bigger deal. Okay, but yeah, they move really, really fast. Okay, really, really fast. All right, questions on either of those? All right, so that was just kind of reviewing V equals 2 pi r over t, or 2 pi r times F. And that one we don't need to do. We'll skip it. We'll skip that one. All right. We want to determine the magnitude of the centripetal force exerted by the rim of a dragster's wheel on the tire. Okay, so when you get tires on your wheels, okay, they have to stick to the wheel. Right? And there's a fair amount of inertia that wants to rip them right off of there. And that's what happens if they get flat. Okay? If your tire gets flat, eventually it just comes off of the wheel. You see that kind of at the end sometimes of police pursuits. Okay, like tires just come right off the wheels, right? Because they've just burned them out, or they've gone over the stop sticks and deflated them, and then that destroys the tire. So what has to happen is there's a combination of two things. First, there's an adhesive that the tire technician will put on the inside of your tire that will actually stick it to the inside of the rim. And then there's the pressure of the air. The air inside the tire pushes the tire against the inside of the rim as well, holding it there. But we need those two things to provide a lot of centripetal force to keep the tire from coming off the rim.
I was always curious for drag cars, when it's, does it bolt to the bead of the rubber, or is there something that you use to keep the tire?
Yeah, it's bolted, yeah, because they can't inflate them all the way. Right, like a dragster's tire, if you ever watch it like in slow motion, you can actually see the tire fold, right, as it starts to spin the first time around. So no, they're not fully inflated. They look all kind of fat, and then as it starts to spin, they get really tall and narrow really fast. Yeah, so they're not. They have to be actually bolted on, because there's not enough pressure inside to pin them against the rim, so they actually have to be bolted to the rim. That allows them to have better traction. Yeah. Okay. All right, so here's what we have. We've got the mass. The tire is 45 kilograms. We know it's rotating at 30.0 meters per second. Okay, and we're trying to find the centripetal force that holds it on the wheel. All right, so centripetal force is mv squared over r. Okay, and sorry, we know the radius too. We know it's 0.480. Okay, so all we have to do is plug in our numbers here. We got 45 kilogram tire multiplied by 30 squared divided by 0.480. So are we looking at a lot of centripetal force? Yes. Whoop, that didn't work. 45 times 30 squared divided by 0.48. All right, 84,000 newtons of force to keep that tire on the rim. That's why they have to be bolted on. Okay, why they can't rely on what our regular tires rely on. Okay. Everybody all right with that one? I would probably never ask you one that easy. You just plug the numbers into the formula. Okay, you guys are too good for that. So, okay, so these two are pretty straightforward. I think we'll do those two, and then we'll see where we're at. Maybe we'll call it a day after those two. Okay. All right, so for question number 2, we got this small pebble stuck in the treads of a dirt bike's wheel. Okay, the radius of the wheel is 23 centimeters. All right, so we got mass, 0.0021 kilograms, and we have the radius, 0.23 meters. And the key is that we have to have that in meters. Okay, and the centripetal force is 0.66 newtons. All right, so we're looking for the speed of the wheel. All right, so we got mv squared over r equals fc. So we multiply both sides by r, divide both sides by m, and square root. All right, so that'll mean we've got 0.66 times 0.23 divided by 0.0021 square rooted. That'll give us our 8.5 meters per second. Okay. All right. Remember that when we come back from Easter, we're going to have a couple of labs that we'll be doing, and your conversion of energy lab is due on May the 1st. That's the Wednesday, so it's not right away when you come back, but that's due when you come back. So maybe have a look at that over the break and get it finished in case you have any questions. Otherwise, have a good Easter break.